Center of mass of a continuous body, rigid body, continuous rigid body. If we consider the body have continuous distribution of matter, the summation in the formula of center of mass is replaced by the integration. That is, RCM vector equals to integration R vector into dm divided by integration dm equals to integration R dm by m. Here the situation is shown. It is a rigid body and we are considering a elemental mass dm any point, and we are taking the position vector of that elemental point is R vector. Then we can calculate the RCM of that rigid body with the rigid continuous body with this formula, where R vector is the position vector of considered elemental mass in component form. XCM equals to integration x dm divided by m, YCM integration of y into dm divided by m, ZCM integration z into dm divided by m, where x, y, z are the coordinate of elements. Center of mass of a rod. Consider a rod is placed on the x-axis with one end at origin of the axis. Consider an element PQ of length dx at a distance x from origin O. Here we are considering a element of length L at a distance x from the origin. Then mass of element PQ will be dm equals to m by L into dx, because the length of considered element is dx. So this represents mass per unit length, and multiply by the length of element will give the mass of element. The coordinate of element PQ are x, 0, 0. Y coordinate is 0 because it is on x-axis, so y coordinate and z coordinate will be 0. Hence, XCM equals to integration x dm by integration dm equals to integration 0 to L, because this element can be considered at this point, at this point, at this point, at this point, and finally at this point. So where our integration is from 0 to L, means at this point the length of rod is 0, and at this point the length of rod is L. So limit is from 0 to L, and here we have put the value of x and the value of dm, so m by L into dx, and divided by integration dm. Equals to m by L 0 to L x dx divided by m, because if all integration of dm will be equal to m, or m by L into 1 by m integration 0 to L x dx equals to 1 by L. After integrating x, this will come out to be x square by 2 under the limit 0 to L, and 1 by 2L solving L square minus 0 square, 1 by 2L into L square equals to L by 2. Now YCM integration y dm by integration dm, 0 into dm, integration dm equals to 0, and ZCM equals to also 0. So the center of mass of the rod, that is shown rod, will be on x-axis at the middle point of the rod. Center of mass of a symmetrical homogeneous body is at its geometric center. That is, if these bodies are symmetrical and homogeneous, then its center of mass will be at its geometrical center. For example, if it is a square plate, then its center of mass is at this point. If it is a cube, then its center of mass is at its geometrical point. Similarly, it is a ring, then its geometrical center. If it is a sphere, then its center of mass is at geometrical center. Find the center of mass of a lamina, triangular lamina. Solution. The lamina triangle LMN may be subdivided into narrow strip each parallel to base MN as shown in the figure by symmetry. By symmetry, each strip has its center of mass at its midpoint. If we join the midpoint of all strips, we get the medium LP. Medium LP. 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 The CM of mass, the center of mass of the triangle as a whole, therefore, has to lie on the median LP. Similarly, we can argue that it lies on the median MQ and NR. This means the CM of mass lies on the point of concurrence of the medians, that is on the centroid G of the triangle. Centroid G of the triangle. Now, motion of center of mass. Let us consider motion of a system of n particles of individual masses m2 dash 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 mn and total mass capital M. It is assumed that no mass enters or leaves the system during its motion, so that m remains constant. Then, as we have seen, RCM equals to m1 r1 plus m2 r2 plus dash 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 mn rn divided by m1 plus m2 plus dash 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 mn equals to m1 r1 plus m2 r2 plus dash 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 mn rn divided by cap m, or equals to multiplying this part into this side. So m into RCM equals to m1 r1 plus m2 r2 plus dash 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 mn rn, equation 1. Now differentiating one with respect to time, m into dRCM by dt equals to m1 dr1 by dt plus m2 dr2 by dt plus dash mn drn by dt, or m and dRCM by dt will give the velocity of center of mass. So we have written m into VCM equal to m1 v1 plus m2 v2 plus dash mn vn. Hence VCM equals to m1 v1 plus m2 v2 plus dash mn vn divided by m, or VCM equals to sigma I equals to 1 to n mi vi vector divided by m for the mv vector momentum of the particle. Hence equation 2 can written as PCM equals to P1 plus P2 plus P3 dash Pn, or PCM equals to sigma I equals to n to n pi vector. Again, differentiating 2 with respect to time, we get m into dVCM by dt equals to m1 dV1 by dt plus m2 dV2 by dt plus dash mn dVn by dt. And differentiation of velocity gives acceleration. So m into ACM equals to m1 a1 plus m2 a2 plus dash mn an. Hence ACM equals to m1 a1 plus m2 a2 plus dash mn an. Sigma I equals to n to 1 MIAI divided by m, equation 4. Now from second law, we know that ma equals to mass into acceleration equals to force. So equation 5 becomes FCM equals to F1 plus F2 plus dash Fn, sigma I equals to 1 to n sigma F5, that is net external force. Thus, the center of mass of a system of particles moves as though it were a particle of mass equal to that of the whole system, with all external forces acting directly on it. Now, conservation of linear momentum and motion of center of mass of n particles. Consider a system of n particles of masses m1, m2 dash mn moving with velocities v1, v2, vn respectively. The momentum of the system is given by p vector equals to m1 v1 plus m2 v2 plus dash mn vn, or p vector equals to or P vector equals to m into VCM, because since m1 v1 plus m2 v2 plus that is mn vm equals to m into VCM, we have calculated earlier, and this equals to P equals to m into VCM, equation 1. Representing 1 with respect to time, we get dp by dt equals to m into d VCM by dt, because m is constant, so it comes out of the differentiation, and dvcm by dt equals to acceleration, so we write m into acm, or dp by dt equals to m into acm, equation 2. Again, we know that net external force on the system is F net equals to m into acm, equation 3. Hence, from 2 and 3, dp by dt equals to F net, equation 4. Thus, the statement of Newton's second law extended to a system of particles. Now, consider that the sum of external forces acting on a system of particles is 0. Then dp by dt equals to F net equals to 0, where F net is your net external force, and this will give P vector equals to constant, because if dp by dt equals to 0, then P will be constant. Thus, when the total external force acting on a system of particles is 0, the total linear momentum of the system is constant. This is the law of conservation of total linear momentum of a system of particles. This also means that when the total external force on the system is 0, the velocity of the center of mass remains constant. Mass remains constant.